let's start unit 2, chapter 1, momentum and energy, in which the first point is conservation of linear momentum. So how do we represent linear momentum? As we know, momentum is a vector quantity. So P bar linear momentum is equal to mass into velocity. So it is a product of mass and velocity. So we know P bar is equal to mass into velocity. So according to Newton's second law of motion, the rate of change of momentum, that is the rate of change of momentum, is nothing but the force applied, the net external force applied on the particle. So this is according to Newton's second law of motion. We know rate of change of momentum is nothing but a net external force acting on the particle. Now if the F bar, that is net external force acting on the particle, is 0, that means dP bar by dt is 0. That is, we know P bar is constant. So from this equation we can say if net external force acting on a particle is 0, then the linear momentum of this particle is conserved. So this is law of conservation of linear momentum. Let's study the conservation of angular momentum, L bar. So consider this diagram. Here a particle is rotating about the axis Z of mass m, and this is angle theta made by its position vector from the origin O. So P bar, we know P bar is a linear momentum of this particle. So P bar, we know it is m dot V bar, and this is L bar, which is perpendicular to both of them, that is position vector and linear momentum vector. So it is, this angular momentum vector is perpendicular to both of these. How do we write this angular momentum? As a r bar cross P bar. So it is a cross product of two vectors, that is a position vector and linear momentum vector, here and here. So that will be the resultant angular momentum. Now we know the magnitude of this L bar, that is a cross product of two vectors. It is a magnitude of individual vector and sine angle. So L bar is rp sine theta. Here we can rearrange this term L bar as a pr sine theta. So this is the magnitude of L bar. Now we know this P as a linear momentum at this point, and r sine theta, here if we consider this as a hypotenuse, this is theta, so sine theta, r sine theta will be this r sine theta. So this is, we know, a physical quantity and a distance about this axis of rotation, so that will be a moment. Now this is moment of linear momentum. So consider this P r sine theta. P is a linear momentum, and r sine theta is this distance. So we know any physical quantity, product of any physical quantity and its distance from the axis of rotation, is nothing but a moment. So this is our linear momentum P, and this product it's showing movement of this linear momentum, which is angular momentum. So this moment of linear momentum is angular momentum. Similarly, moment of linear force is a angular force, which is torque. So these are the physical quantities related to movement. That is, movement is a product of distance and any physical quantity, distance from axis of rotation. Now we know by Newton's second law of motion, force is nothing but rate of change of linear momentum. So we just multiply both the sides with r bar. So taking this cross product or vector product on both sides, r bar into r bar cross f bar is equal to r bar cross dp bar by dt. So say this equation 2. Now we know r bar cross f bar, it is a moment of force which is nothing but torque. So r bar, this equation becomes torque is equal to r bar cross dp bar by dt. Now differentiating equation 1, here we have the equation 1, L bar is equal to r bar cross p bar. So differentiating this equation by parts, we know derivative first term, into second term as it is plus first term into derivative of second term. So we know this. Now this dr bar by dt, we know change in distance with respect to time, change in as r bar is a vector quantity, here it is a displacement, so change in displacement with respect to time is a vector quantity, that is velocity. And we know momentum as mass and product of mass and velocity, also this term as it is. Now here it is a cross product of two vectors, this is a constant, so v bar cross v bar is nothing but, that means I bar cross I bar, we know it is 0, so this term gets cancelled out and we get dl bar by dt is equal to r bar cross dp bar by dt. Now compare this equation 3 and equation 4, we see RH is same, so LHS should be same, that is tau bar is equal to dl bar by dt. So we are just comparing equation 4 and 3. So we got the relation tau bar is equal to dl bar by dt, that is torque is nothing but rate of change of angular momentum. So if the net torque acting on a particle is 0, that is tau bar is equal to 0, that means dl bar by dt is equal to 0, that means L bar is constant. So this is that means L bar is conserved. So this is a law of conservation of angular momentum. Let's study the work energy theorem. Here F bar, which is a function of r, that is a distance, is force acting on a particle. So if the particle makes displacement, small displacement dr bar, then the small work done will be F bar dot dr bar, that is a product of force acting on the particle and the displacement. Now if you want to calculate a total work done from position 1 to 2, if a particle makes a displacement from position 1 to 2, then the total work done, that is a complete work done, we have to take integration of F bar dot this small dr bar, small displacement from 1 to 2. Now Newton's second law of motion. So first see here is work done, the total capital W, the total work done is F bar dot dr bar, which is a dot product of two vectors, but in this case we have taken both are in same direction, that is force and displacement are in same direction, that is I bar dot I bar is equal to 1. So we can treat it like a regular product F dot dr. Now according to Newton's second law of motion, we know force is mass times acceleration. So mass and product of acceleration nothing but rate of change of velocity with respect to time, so it will be mass into dv by dr into dr by dt. We know we can write this equation like this because we need this quantity. Okay, so mass into this v bar, here dr bar by dt is nothing but velocity, rate of change of displacement with respect to time, and dv bar by dt as it is. Now this equation 1, our equation 1 becomes with this value, because F bar is mv bar dot dr bar dt, so we put the value here and we got this equation. W is equal to capital W is equal to integration from 1 to 2 mass velocity into dv bar by dr into dr. So this dr gets cancelled, and here again we can see this I dot I, so we can treat it as a regular product. Now taking this integration of mv with respect to dv, so mv square by 2, we know this integration, definite integration, putting the values we get the t2 minus t1, that is a change of kinetic energy. We know this is a kinetic energy, so this is change in kinetic energy. So work done, we just proved the work energy theorem, that is work done is nothing but a change in kinetic energy. Let's study the conservation of energy for a single particle. After some time we will study it about a system of particles. Now for a single particle. So conservative force, we know what is the conservative force when the total work done in one round trip is 0. That is, it doesn't depend upon the path followed. And the non-conservative force, in which the total work done in this total one round trip, if it is a non-zero, then there is some loss of or conversion of energy, then we say it is a non-conservative force. That is, the path followed, the energy or the work done, the total work done is depends upon the path followed in the process. Let's take another example of conservative force with the gravitation. So consider particle is here at position A. Consider this point C and B. Consider a mass M at this point A, point B and point C. Now let's say this is a one path we are going to follow. Let's say the work done in this path against the gravitational force, because we are increasing the height, so the potential energy will be increased. So we are doing the work done against the gravitational force, so that will be omega 1, and let's say a path second A to B, B to C. So let's say work done in this process is omega 2. Now the we can prove this mathematically. This omega 1 and the second path from A to B, B to C, the work done is same. It's same, and it only depends upon the initial and final positions. Does not depend upon the path followed. So we can say it is a conservative force. In this case, it is a gravitational force. Now, if it is a non-conservative force, then the path followed is matters. For example, if you are here and here it's second point B, you choose this shortest path, then the forces will be, the work done will be smaller in case of frictional force. Okay, we are taking non-conservative force example as a frictional force. So if you choose this path, the friction will be less because the path is lesser. If you choose this path, then it is a path, as path is a bigger one, so the friction will be greater, and hence the work done must be greater. So it depends upon the path followed, and hence it is a non-conservative force, that is a frictional force. Study the conservation of energy. So in work energy theorem, we know that is work done from a particle moving from position 1 to 2, and the force acting on the particle is F bar. Then we can write the work done on the particle from position 1 to 2 as a product of force and displacement. Okay, so we take the integration over this small displacement from position 1 to 2. Now in work energy theorem, we know the total work done is T2 minus T1, that is a change in kinetic energy of that particle. If forces acting the body or the particle is conservative, then we know the change in kinetic energy is equal to change in potential energy at any point. The forces acting on the particle are conservative, then the change in kinetic energy is equal to change in potential energy. Now we know change in potential energy. Here from equation 1 we can compare these two equations and write total work done is a change in potential energy of that particle. So from equation 2 we can write the equation 3. So consider if the forces are conservative. So for conservative force, we can define the potential as a negative gradient of potential. We know this in vectors. So it is a negative gradient of potential, that is a conservative force. So we write it as a minus of del u equal to, or the gradient of u is a minus du by dr. Now from equation 3 we can write we just put this value of force in that equation and calculate the integration. So we get the work done as a change in potential energy. So we can equate the, so from equation 1 and equation 4 we can write T2 minus T1 as U1 minus U2, because work done is same here. So T1 plus U1 is equal to T2 plus U2, that is constant. We can write it from here. So we know sum of potential energy plus kinetic energy is nothing but E, that is the total mechanical energy, which is constant here, we can say, because it is this point at the position 1 at the position 2 they are same, equal. So that means the mechanical energy is constant, which is conserved. That means it is conserved. Now if the forces acting on the particle are non-conservative like friction, then the energy will transform from one form to the another, but it will not get destroyed, because the law of conservation of energy. We know the energy cannot be created nor destroyed, it just transforms from one form to another. So let's study center of mass. Consider 2-point particles, 2-point masses m1 and m2 at a distances x1 and x2 from the origin. And suppose the whole mass of the system, that is m1 plus m2, is concentrated at this point, which is center of mass. So at this point where its distance from the origin is x cm, that is center of mass. Let's write mass moments. So we can write mass moment at this point as a distance and the total mass. So total mass we know m1 plus m2, that is a point where we are supposing the whole mass of the system is concentrated. So this mass and distance from the origin. Also here we can write again for this we have written for total system. Now individual mass moments, like for this particle and this particle, so that will be the whole system's mass moments. So we are just writing m1 x1 plus m2 x2, and their addition will be a total whole system's mass moments. So this is a mass moment of a whole system, this is also mass moment of a whole system. So we can define the position of center of mass, that is distance from the origin, as x cm is equal to m1 x1. So just we are rearranging this equation, m1 x1 plus m2 x2 by m1 plus m2. Here m1 plus m2 is nothing but capital M, that is the whole mass of the system, because in system we have only two masses, m1 and m2. Now for similarly we can generalize the formula for n particles, as here you can see all of the particles are taken, all the mass, individual masses are taken. So, summation over I mi dot ni, sorry, xi divided by the whole mass of the system again. So in 3D space we can take y axis also and z axis also. So that will be like all the three axes we are considering. Now we know the r bar, we can write it as a in its terms of rectangular components. So I bar x plus j bar y plus k bar z. So we just take the position vector of our r bar, that is the center of mass, and we write all the rectangular components, that is x cm, y cm and z cm, and their respective unit vectors along these respective directions. Realize it as a the summation over mi ri. So we can take this radius vector, position vector of the center of mass like this. Now if the whole mass is distributed uniformly, then we can make the small divisions of total mass like dm, and we can replace the summation sign by integration like this. So here we can again write the position of center of mass, the position vector, in terms of a smaller divisions of a total mass, whole mass. Let's see the physical significance of center of mass. Consider n particles having masses m1, m2, m3 up to mn. Now we know how to write their mass moments, like mass and the distance from the center of rotation. So that is m r bar by r bar cm, that is a position vector of center of mass, where the center of mass is located, and this is the center. This is a mass of a whole system. Now we, in the RHS side, we just write it in terms of individual components, like m1 r1 square, that is mass of a first particle and its distance from the origin or the axis of rotation. So we just write them in their individual components. Now after differentiating this equation, we know that is a dr bar cm by dt. So similarly on the RHS side, now we know this is nothing but a velocity. So we just write a velocity component there. So here this is the velocity of center of mass, and here the velocities of individual particles or individual masses. Now similarly we can differentiate this again for velocity. Okay, so we are just differentiating it, double differentiation. So here velocity, the derivative of a velocity with respect to time is nothing but acceleration. Similarly on the RHS side, it is a1 for that is a velocity, that is the acceleration of individual particle. This is acceleration of a second particle. This is acceleration of a nth particle. Now this a is a acceleration of a center of mass. So according to Newton's second law of motion, we know mass into acceleration is nothing but force. So this is a force on a center of mass, okay, and this is a force and individual, that is F1 plus F2. So individual particles, the forces acting on individual particles. Now we are considering only the external force, because the internal forces acting on a body cancel each out other, because they are always in a pair and in opposite directions, so they cancel each out. So only force remain on the body is nothing but external force, net external force. Now consider the conservation of linear momentum for a system of particles. So consider n particles having masses m1, m2 up to mn, and with velocities v1 up to vn, and hence we can write their linear momenta as p1, p2, p3. So we know p1 is a product of m1 and v1, so that is mass and velocity. Now we can write total momentum, that is linear momentum of the system, as p bar is equal to p1 bar plus p2 bar plus p3 bar up to pn bar. Now we know we can write p bar in terms of a mass and velocity also. So just putting the values of momenta here, m v c v centimeter center of mass, that is a velocity of center of mass. So writing all these values, we get this equation. Now consider this diagram here. Here we are having system of particles. Three particles are here with masses m1, m2 and m3. Now the internal forces, the internal interacting forces on these particles are F21, that is a force by 2, that is particle 2 on particle 1 is in this direction, and its value is F21. So similarly this particle also will apply force on this particle, so that will be for F12, that is a internal forces of these particles. So similarly for these two particles there will be forces F31, F13. Similarly for this and this particle, so these will be the internal forces, but we know these forces cancel each out because they are in pair and they are opposite in direction, hence their value, their magnitude is same but their direction is opposite. So they will cancel each out, and only the remaining forces will be these external forces, that is F1 bar, F2 bar and F3 bar acting on individual particles. So the resultant force will be only the external force. Internal forces will cancel each out. So external force, we will just take the vector sum of all these three. So for example here, if this is a F1 force acting on particle 1, this F2 bar is a force acting on particle second, and this is a force acting on particle third, then by vector law of addition, triangle law of vector addition, we can just take the resultant, that is F bar is equal to F external. So it is a summation of only external forces. So F bar, we can write the F bar, force acting on system of particles, is nothing but F external, that is sum of F1, F2 up to Fn. By Newton's second law of motion, we know force is nothing but mass into acceleration. So mass into acceleration is nothing but rate of change of velocity with respect to time. Again take this m inside, and we know mass into velocity is nothing but linear momentum. So we got the equation F external is equal to rate of change of momentum. So if the external force acting on a system of particles is 0, then the P bar is constant, we know, so it is conserved. Now we can say the vector sum of moments of all the particles in the system remains constant when the external force acting is 0. Now let's study conservation of angular momentum of system of particles. Consider n particles with their angular momenta as L1 bar, L2 bar up to Ln bar. Now we can write the total angular momentum of the system as capital L bar is equal to summation of all these individual angular momenta. So similarly we can write this L bar in terms of a torque. Okay, so we know rate of change of angular momentum is nothing but torque. So for the individual particles it will be like the tau 1 plus tau 2 plus tau 3 up to tau n. Now we know tau total is nothing but tau internal plus tau external, but again in this case also the internal forces acting on particles are equal and opposite in direction, hence they cancel each out. So similarly, the torques also cancel each out because there is no net internal force acting on the particles. So the torques will also get cancelled because torques are result of these forces. So the torque gets cancelled, internal torque. So only the external torque remains. So we can write tau bar external is equal to dl bar by dt. That is a total rate of change of total angular momentum is nothing but due to the external torque. So if the net external torque acting on system of particles is 0, that is dl bar by dt is equal to 0, that means L bar is constant and hence it is conserved. So we can say the rate of change of total angular momentum of system of particles is vector sum of all the individual torques. So the external individual torques acting on the system of particles. Now let's study the conservation of energy for a system of particles. Consider n particles with masses m1 up to mn and velocities up to v1 up to vn. So we know the total kinetic energy of this system of particles will be capital T is equal to summation over I half mi vi square. So let's say this equation 1. Now we know the total forces acting on the ith particle is a function of the position of that particle from all of these particles in the system. For example, consider this system of particle, okay, and let's consider this particle I. So the force acting on this particle depends upon all the particles in this system, because the distance, and that is the distance r1 from the individual. For example, let's say here is particle 1. So this distance matters because the force acting on this particle is a function of distance, okay, distance between this particle and other particles. So this force acting on this ith particle is a function of all these small or individual distances of other particles in the system. So we are considering a conservative system. So for conservative system, the potential, we know the potential is a function of position. So we know we can write this force acting on ith particle for a conservative system. We can write it as the negative gradient of potential, that is ui. We are taking ui as a potential. So the equation for motion of ith particle we also can write using this equation, that is a force is mass times acceleration, rate of change of velocity with respect to time is nothing but acceleration. So we got these two equations 2 and 3. So we know the LHS is equal, so the RHS must be equal. So that is mi dot d ui bar by dt is equal to minus of that is negative gradient of potential. So just multiply here with vi on both the sides, vi bar, that is we are taking a scalar product with respect to vi on both sides. Now if we calculate both these equations 3 and 4, to solve this, just consider a derivative of vi bar with respect and vi bar. So we know it is vi square. For RHS side, it will be a derivative by parts. So that will be 2 times vi bar dot dvi bar by dt. But we know this 2 can be here because it is a constant. So we will write this equation as vi bar dot vi dvi bar by dt is equal to d by dt of vi square by 2. Now we will use this equation, that is this value in here, this equation number 4. So this equation number 4 becomes here, if we write this value in this equation, this value, that will be d by dt of half mi vi square is equal to this RHS of the equation number 4, that is minus d ui by ui bar ui by dri into vi. It is vi, okay, vi bar. So we know what is vi bar. It is a rate of change of displacement with respect to time. So we just put the value of vi here and we get the equation, because this dri gets cancelled and we get minus dui by dt. So this equation 4 becomes like this. But this is for only ith particle, any single particle, any ith particle. So for a system of n particles, we need to take the summation on both sides. Now the differentiation can get outside and the summation sign can come inside, so we'll just rearrange the equation like this. But we know summation of this is nothing but quantity capital T, which is the kinetic energy of all the system of n particles, and this is nothing but a potential energy of this n system of n particles. So this rearranging this equation, T minus V, so it will be T plus V. So derivative of this term is 0, that means this term is a constant, so the total energy of system of n particles is conserved. This is a law of conservation of energy of system of particles. How do we see the rocket? Rocket is a variable mass system in which fuel gets burned and hot gases are ejected from a small opening at high speed. So rocket gets into the space. Now what happens here? It is action, and the rocket drives on the Newton's third law of motion, that is every action has equal and opposite reaction. So rocket here high speed gases are ejected from a small opening in reverse direction. So in the given direction we will get a reaction force. So the this is a rocket and it is a variable mass system. Now what happens, we are taking a mass of the rocket as capital M and velocity V at time t. Okay, after time interval t, the mass will reduce because the gases are burning and getting out, the fuel is burning, and the hot gases are getting ejected from the small opening from the rocket in the opposite direction, that is u bar, that is the velocity of the gases. So change in mass is del m, and increase in velocity, because mass is decreased, so the velocity will get increased, so that is a del v bar at a time del t. So let's find out the equation of motion for the system of particles. Now let's consider any force, external force acting on the rocket, which may be drag force or gravitational force we can say. So using Newton's second law of motion, we know rate of change of momentum is nothing but force. So final moment, what is the rate of change of momentum? We can write it as a initial moment, final momentum minus initial momentum, so that will be change divided by the change in time. So that will be rate of change of momentum with respect to time. Now the initial momentum of the rocket we can see in this diagram, rocket or system, because we are considering this whole system. In this case also we are considering the hot gases and this rocket as a whole system. Okay, so if we consider angular momentum of this part, we have to consider angular momentum of this part, also the linear momentum, also the energy of this part. The whole system we are considering, not simply the rocket. We are considering this exhaust gases also. So this is a complete system. This is a system. Now so the initial momentum was capital M into V bar. This is also capital M. So the initial momentum was of the system was capital M into V bar. Then the final momentum was after time del t was the moment mass. This is a mass of rocket, reduced mass due to the gases, and this is increased velocity due to these exhaust gases. Okay, so this is this mass of rocket, this is velocity of rocket, so take their product, plus we need to consider the momentum of these gases also, because we are considering system, the whole system, we are studying the whole system. So we need to add this momentum also, because the final momentum we are considering all the system. So we just add the momentum of the gases also. Now let's put these values in this equation. So we will write it like this, and just solve these two brackets. So multiply this m with this whole bracket, we will get m v bar plus m del v bar, and del m into this whole bracket as it is. So here we will get the common terms m v bar here and this m v bar, so they will get cancelled and we will get this equation. So here just take these commons outside and these terms as it is. Now here this term is nothing but relative velocity of gases, relative velocity of gases. Consider this note here, you will understand what is concept of relative velocity. Consider a rocket with rocket A is a rocket, not simply a rocket. Consider a particle moving with velocity 1 meter per second, and consider second particle with velocity 3 meter per second. So relative velocity of A with respect to B is nothing but 1 minus 3. That means we are considering its relative velocity with respect to this. We are considering B as a stationary and measuring velocity of this particle. Or if you want to find out velocity of this particle with respect to A, that means we consider A as a stationary one and measure the velocity relative to this. So its velocity will be 3 minus 2, that is difference between them. If we are finding relative velocity of this with respect to this, we need to subtract this value from this, that is 3 minus 1 will be 3 minus, there's a writing mistake here, I will just clear it out. So that will be 3 minus 1, 2 meter per second. That means it's really, if we consider it is as a reference frame, the velocity of B will be 2 meter per second, because this one and one from this one will get cancelled and we'll get only 2 meter per second, as we consider A as a stationary frame or reference frame. Now if you consider A as a reference frame, B as a reference frame and measure velocity of A, then it will be minus. Now due to this relative velocity, the equation 2 becomes like this. So this term is nothing but thrust experienced by the rocket, okay, because it is a momentum, we know mass, rate at which the momentum is transferred to the rocket by the mass, that is thrust, we know. So as it is mv bar into d by dt, that is rate of change of momentum, or we can say the rate at which the moment is transferred from the rocket to the rocket by the mass, that is a thrust. So thrust, we can write this term as a ft bar. Thrust is also a force, okay. dm by dt is negative because the rate of change of mass with respect to time is not a positive. The mass decreases with respect to time. As time increases, the mass of the rocket decreases, hence this term, the rate of change of mass, is negative. Hence we put this value in this equation, then this term gets to this side. So ft bar is a minus, so after rearranging the term it will be plus. So this is the equation of rocket.